percent in list prepared by Stratford University, and top 500 in meteorology and atmospheric sciences in 2020. With rich professional experience as a visiting professor in Indo-US Warri Fellowship, with rich professional experience as a visiting professor in Indo-US Warri Fellow, University of Nebraska-Lincoln, USA. He has also worked as a visiting professor in Aristotle University of Thessaloniki, Greece, postdoctoral fellow in McGill University, Canada, postdoctoral fellow in Nanyang Technological University, Singapore, research assistant in the University of Waterloo, Canada, and he has also worked as a manager in CNIA, Bangalore. That's a brief work profile. His books are on fluid mechanics, hydraulic machines, engineering, hydrology, sustainability, fundamentals and applications, integrated risk of pandemic COVID-19 impacts, resilience and recommendations. Lot of publications with including patents, textbooks, and he has guided various research students in the post-graduation and PhD as well. He has 4 research grants. He's an editorial member of various journals. Presently, his current research interests are climate change, hydrology, glaciology, irrigation, carbon sequestration, and data mining. He also has been awarded by a lot of honors as Professor S.N. Gupta Memorial Lecture Award, Best Researcher of the Year Award in 2020. He's been awarded as Visiting International Fellow in 2019. Professor R.J. Garte Research Award, Best Theoretical Oriented Paper Award in 2018, IEI Young Engineers Award, Outstanding Young Scientist and awarded first runner-up in the Asia Pacific Network for Global Change Research in Japan, PRNS Young Scientist Research Grants, SGSITS National Award for Best Research Work by Young Teachers, NIT Warangal Distinguished Young Alumni Professional Achievement Award, Indo-US Warri Fellowship Award, DST Young Scientist Fast Track Grants, Inspire Faculty Fellowship Award, Erasmus Mundus Interweave Award, Europe, JSPS Fellowship Award, University of Tokyo in Japan, Travel Fellowship Award by Colorado, USA, Postdoctoral Fellowship Award, McGill University, Canada, Young Scientist Award, APEC Climate Center, Republic of Korea, Travel Fellowship Award by Republic of Korea, Postdoctoral Fellowship Award by University of California, and Canadian Commonwealth Scholarship Award by University of Waterloo, Canada. We are indeed privileged to have you, sir, and thank you so much for accepting my invitation and taking time out your busy schedule. I request, sir, please start with the technical session, sir.
Thank you very much, Dr. Devanshi, for inviting me and IPS Academy to have this wonderful course. And I hope, I think yesterday was the first day and today is the second day for the course.
Yes, sir.
You have, I think, around 100 participants are there. I can see it. Yeah. So
So registered are around 500, but those people who are attending are around 100.
yeah. Sometimes in the online it will be difficult. They don't have internet connection and all kind of
Yes.
problems. But yeah, I think it's a great. So thank you so much for inviting me on my behalf at IIT Indore. Thank you so much, Dr. Devanshi and IPS Academy. So let us
Thank
go
you,
ahead
sir.
with the presentation and yeah. Okay, so I hope you can see my screen.
Yes, sir. It's
Okay,
visible.
okay, okay. So I will talk about a little bit of the climate change and the water resources, and we will discuss the things that we are seeing in the newspapers on day-to-day basis. You may have seen there is a flood in the Bihar, Maharashtra, and several parts of India in the yesterday's headlines and day before yesterday's headlines. So why this all these problems are occurring? You have an intensity, high intensity of the rainfall, extreme rainfalls, and how this is affecting our water management, water bodies, and in general populations. If you remember, in July 2005, there was um, rainfall of approximately 94 centimeters in just 18 hours. and that created havoc in the Mumbai city, and that is the India's financial capital. If you remember another incident that happened in somewhere around 16th June 2013 in Uttarakhand near Kedarnath temple. So in 72 hours, there is approximately 38 or 39 centimeters of the rainfall. In another incident, if I can remember, in Chennai, November 2015, in 48 hours, we got around 48 centimeters of the rainfalls. And in August 2018 in Kerala, you got a rainfall of around 31 centimeters in just 48 hours. So that kind of magnitude of rainfall is occurring in the short events. And obviously, if that amount of rainfall occurs, we don't have that much of infrastructure that can go up and the water can go to out of the catchment. So naturally, inundation will happen, and we all have the problem with that. So all these, why this have been occurring and why these are phenomena occurring recurrently and frequently. What are the reasons for that? So we will try to discuss all these stuffs and based on the current climate change scenarios. Okay, so here are the few news that you may have seen in the newspapers. There is a flood there, there is a drought there, and how all these extreme events of drought, flood, they are occurring our economy. So let us talk about from the basic, what is the basic difference between weather and the climate. If I talk about the weather on the time scale, we will talk only for minutes, hours and days. How's the weather? If I talk about the climate, it go beyond the decadal scales. So there is a difference between the time scale here. Another thing is the spatial scale. And the spatial scale, if I talk about the weather, it's on the local scale or regional scale. If you talk about the climate, it's on continental scale or the global scale. So these are the basic difference between weather and the climates. And how we will define the climate change? If there is any long-term significant change in the average weather in the given duration of the time of 30 years or a century scale that a region experiences, then we will say is the average weather will deals with the average temperature, average precipitation, average wind patterns, or many other stuffs. So I hope the definitions of weather and climate, climate change, average weather is getting clear. So what are the elements of weather and climate that affect these kind of conditions? Obviously the precipitation, the rainfall that we have, the temperatures, wind, atmospheric pressure, clouds and humidity. So these are the primary 6 elements that affect our weather and climate of a given conditions or of a given regions. And if we talk about the elements, now we talk about the controls, which how the controls of these weather elements, which are the important parameters or the factors. So at what kind of latitude and altitude you are located. So whether you are on mid latitudes or high altitudes, so that will determine the weather and climate of that region. Another thing is that on the earth we have the several oceans and lands. So unequal distributions of these lands and water, that is also creating the control in terms of weather and climates. Another things you have anthropogenic activities like human induced activities in terms of industrialization, deforestation, construction activities, urbanization. So they also have the impact on this control of weather and climates. Another thing, the orientation. So whether it's you are on the leeward sides or windward sides. So based on that orientation of the mountain. So based on that, whether you are getting rainfall or not, that will also determine that. Another thing is the ocean currents and the nature of the ground surface. So these are the primarily 7 to 8 factors that will control our weather and climate, and ultimately that will results in the precipitation, temperature, wind patterns, and all these stuffs. So emission in the greenhouse gases and ozone depletions. So that basically changes the global radiation balance and the climate change, and that affect the glacier extent change, deglaciation, sea level change, frequently occurring droughts, floods, and other such extreme events. So that's how all these things are linked with each other. So with this summary, I think climate is nothing but an average weather. So climate is like a statistics of the weather, which include the variability in terms of 30 years or the centurial scales in terms of average temperature, average precipitation, and other parameters. And just I talked about the extremes. So climate extremes are the extreme statistics of the weather which are unexpected, like rainfall in Uttarakhand in June 2013, unusual, severe, and unseasonal weather. So these are some of the climate extremes examples and how they are being results. So I just mentioned to you that rise in the greenhouse gas emissions, land use and land cover changes, industrializations, urbanizations, all these things are affecting the hydrological cycle and they are intensifying the hydrological cycle. And once you are intensifying the hydrological cycle, it is affecting the intensity, duration, and frequency of extreme events, either drought or flood in the present and the future. Okay, now I will give you just a brief idea how India is impacting on the climate change and how our water resources has been impacted on the climate change. Because in the climate change, there is a direct and indirect effect that have an adverse impact on water resources, human system, regional agriculture, and the food security. In India, we got like 1.3 billion population, and that is around 17% of the world population. And how much world water resources we have? We have only 4% of world water resources. What's arable land? We have only 9%. And population, we have around 17% of the world. So with 17% of the world population, we need to we have only 4% of the world water resources and 9% of world's arable land. With these two parameters, I need to feed 17% of the global population. So that kind of parameter exists as on today. And with these constraints, we also have another constraint like rainfall. If we talk about the Northeast India, we have a highest rainfall receiving region near Cherrapunji, Mehsram. In contrast, we also have the Thar Desert in the western India, in Rajasthan, where you are getting only 10 centimeters of the rainfall or 20 centimeters of the rainfall. So spatial distribution is highly uneven in terms of rainfall. Similarly, the temporal, whatever rainfall we get across the year in the 4 months, 1st June to 30th September, we are getting around 80% of the rainfall. And if we see the trend in last 20 years or last 10 years, most of these rainfalls are occurring in the month of August. June, July, and September rainfall has been reduced, and maximum rainfall has been occurring in the month of August. So whatever comes in the 4 months, now it's coming in 1 month or the 2 months. So the temporal distribution is also uneven, spatial distribution is also uneven across the India. Another, there has been a significant change in the precipitation and temperature during 2000 to 2015 in India in comparison to the last 100 years. And that we can include as one of the signature for climate change in India. If you may have seen the recent reports of Niti Aayog. Niti Aayog says that around 5,500 crore rupees we are in the loss every year due to these extreme events of floods, and approximately around 1,500 people they have been died every year due to the floods. Like there are few another instance like 2016 there was a drought, and that drought covers the 10 states. And if it affected around 33 crore people and caused an economic loss of $100 billion. So you have an economic loss, you have people's loss, and people are suffering, and a vast geography is suffering. Like around 14% of Indian geographical area is subjected to the flood disasters. And 33 million people have been affected by the flooding from 1953 to 2000. And if I give you the recent data, like around 44 crores hectares of area has been affected by these floods or heavy rainfalls. and around more than 20 crores people have been affected from 1953 to 2021. And we talk about average annually around 30 lakhs people are have been affected by these rainfalls, extreme rainfalls or the flood across the India. So it's a big number. So people have to deal with all these extreme events, and as a scientist and as a researchers, how we can help in terms of policy or in terms of early warning, giving the right information insight so that the people can people things infrastructure that can be managed. Uh, if we talk about the groundwater, in northern India, groundwater storage has been decreased at a rate of 2 centimeters per year. However, in South India, there have been increase in the 1 to 2 centimeters per year between 2002 to 2030 based on GRACE data, gravity, recovery, climate experimental data. So in India, we have all kind of stuff, so drought, flood, groundwater changes, because India got a multifaceted geography. And each region has a different type of the climate. If we talk about the northeast, they have the different climate compared to the western part of India. If you go to the top, Jammu and Kashmir, Himachal Pradesh, they have the different climate compared to the peninsular India. So every climate has substantially different things, and different river basins, they have the each characteristics. So all these cannot be generalized for across the India. We need to make the special planning for the region specific. Let us talk about the rainfall, because in this course we are talking about the water quality and water bodies. So how the rainfall, because if you don't have a rainfall, we cannot talk about the water quality and water bodies. So how the rainfall is changing. As I mentioned, that in India we are getting around 80% of annual precipitation due to southwest monsoon between June to September. And if we talk about 306 stations across India with 135 years of data, 1871 to 2005, no significant trend is observed in annual rainfall on national basis. So it says the total amount of precipitation has not much changed. However, a small decreasing trend in annual rainfall was observed across the India, whereas a small increasing trend is observed in the northwestern and peninsular India. So there are few kind of trends in the region specific. In the several major river basins, number of rainy days has been increased while the number of intense events have increased. So number of rainy days, they are decreasing, but number of intense events, it means the amount of rainfall I am getting one day has been increased. So intensity of the rainfall has been increased. And here you can see the mean annual precipitations and annual precipitation from 2000 to 2015. So it's around 110 centimeters. What about the temperature? How the trend of the temperature during last 100 years or 115 years? And generally, a warming trend across the India has been observed, with 2016 as the warmest year on the record since nationwide record commenced in 1901. And the national average annual temperature showed an increase of 0.22 degrees Celsius per decade during 1971 to 2003. So you have a warming of around 0.22 degrees Celsius per decade. An increase in the mean temperature has been observed across India for a period of 107 years, with highest rise in western Himalayan region. So location specific here. So western region have increased the mean temperature while you compare the rest of the India. An increase of 2 to 4.8 degrees Celsius in average weather across India is expected using 18 CMIP-5 models from 1880s to 2080. So CMIP-5 are coupled model intercomparison project of general circulation models. So 18 GCMs were taken, and up to 2080, the next 50 to 60 years, they have estimated there is an increase in the 2 to 4.8 degrees Celsius. I'll give you some kind of brief of general circulation models in the next slides. And here are the projections for mean temperature and minimum mean maximum temperature and mean minimum temperature. So mean maximum and mean minimum temperature, they have also been increased about 0.28 degrees Celsius and 0.22 degrees Celsius in last 15 years, means 2000 to 2014. Okay, we have talked about the rainfall, we have talked about the temperature, how the river runoff. If I talk about the river runoff, in northern part of India, there is a declining trends in 41 years from 1971 to 2010 of daily stream flow records for Satluj River have been observed at 3 gauging stations, Kasol, Sunni and Rampur. And the basin has an importance and the high potential for hydroelectricity power generation and agriculture practices. So if there is a declining trend and you have an agriculture and hydropower, it may create problems. Another significant declining trends in mean annual stream flow in the Byas River and a decreasing but insignificant trends for Ravi River has been observed. In Peninsula, if we talk about Mahanadi River basins, the stream flow has declined at a rate of 3,388 million cubic meter per decade for a period of 1972 to 2007. However, there are increasing trends in the particular regions of Brahmaputra. The Himalayan river basins such as Brahmaputra, Indus, they are projected to have a reduced upstream flow based on GCMs for SRES A1B scenario over the period of 2046 to 2065. So this is about the runoff, rainfall, temperature, river runoff, and let us discuss something about drought so that we will cover whole integrated things. Drought is a especially extensive events that affect the large number of populations in India every year. Around 33% of India's geographical area is vulnerable to these drought conditions. If we see over the last 5 decades, very severe drought hits India in 1960s, 1965, in 1970s, 1972 and 79, in the late 90s, 1987 and late 2000s in 2009, where more than 40% of India's geographical area was affected. And Indian Meteorological Department, IMD, identifies the arid western meteorological subdivision. It means western Rajasthan and Saurashtra, Kutch, the most drought affected region in India with 31 drought events during 1875 to 2004. A analysis has been done to divide approximately 35 years from 1901 to 2004, and there is an increasing trend in terms of drought severity and frequencies find out in the 1972 to 2004 in comparison to 1901 to 1935 and 1936 to 1971. And there is a increasing in the severity in the meteorological, vegetation and short duration droughts in comparison with year-long droughts figures in the last 3 decades. Here you can see in this picture drought conditions across 566 stations were accessed determined using SPI, Standardized Precipitation Index, and the 6-month SPI series were calculated at all stations using monthly rainfall data over 102 years. And there are the increasing trends have been found out in northeastern, central eastern, southern parts, and the decreasing trends have been found out in western, northwestern, and southern regions. So this is about the drought, and then because India got around 9,000 glaciers, and which covers more than 18,000 square kilometers of area in Indus, Brahmaputra, and Ganga river basins. So let us discuss something about the glaciers as well. And the changes in the glacier and its extent can influence the river runoff and the availability of the water in the Himalayan rivers like Indus, Ganges, Brahmaputra, which are very crucial for hydroelectric power, irrigation, and for drinking water, industrial water supply, and agriculture development, especially in the part of North and Northeast India. So there are few mass balance studies have been done on these glaciers, and there are evidences of long-term mass balance support in net loss for Indian Himalayan glacier for last 4 decades, varying a few. The few examples are here. The annual rate of glacial sinkage is about 0.2 to 0.7% in the Indian Himalayan region for the 11 river basins with a period of 1960 to 2004, and the mean extent was somewhere around 0.32 to 1.4 square kilometer. And if we talk about this Chota Shigri Glacier, around 15.7 square kilometers, that is located in Chandra River Basin in Himachal Pradesh, showed a net loss of about 1000 meter during 2002 to 2009. The temperature reconstructed over the last 400 years using the tree ring width data in Gangotri Glacier in Western Himalaya indicate increased winter temperature is attributed to high glacial retreat. So there is an increase in the winter temperature, and that has been one of the reason or one of the cause to melt the glaciers. And this is another study in the Jemu Glacier in the part of the Sikkim region, Himalayan region, where there are two things were considered. Like one is the surveyed topo sheet of Jemu Glacier region, 1935. Another is the list 3 image, linear imaging self scanner list 3 from ISRO classified map 2014. And once the both are compared, there is a found a reduction in the snout portion in comparison to 1935 image. So some of these examples that I gave here from Western Himalayan region, and some of these are from Eastern Himalayan region based on the glacier melts. So what are the implications of these climate change and the water policy and the climate change policy? Because India got a 17% of the world population and 30% of the global poor population, agrarian economy, large coastal line of around 7,500 kilometers. North you have a Himalayan, south you have an island, west side you have a desert, and the northeast you have a highest rainfall receiving region. So how we can manage the water in these terms? So first of all, national water policy that came in existence first in 1987, then it was came in 2002, and all these things have been happened, but all these different policies adopted by the government at different levels, they have been sometimes remain inconsistent, somewhat adequate, because of various elements such as local, regional, national, and international, and their enforcement issues. So what we need to have the future water resources problem, to combat them, we need to have a strengthen to assess the good quality data. Many times the data is not available. Sometimes it's available, it's not a good quality data that can be used for modeling and physical mathematical studies. So to assess the good quality data, we need to upgrade the data collection systems, network storage, and promote the multidisciplinary approach in order to have the different parts of the country. And that's how we can assist in making the scientific decisions on water and the climate change policies. So what we can take it forward from there? Because we need to assess the impact of the climate change, we need to adopt the techniques in order to assess the water quality, water bodies, and how the things are happening at the local levels. So there is a national action plan on the climate change that was launched in 2008 that will determine the strategies to address the climate change impact, mitigation, and the adaptation. And there's a 20% improvement in water use efficiency and expanding the forest cover from 23 to 33% on India's territory in the long terms. Another example that I can give you, there is a kind of flood plain zoning act in 1975, around 45 years back. There was a model draft that was prepared by the central government, and it was sent to all the states to uh, to assess and to enact on that. But some states like Manipur, Rajasthan, they made the act on based on this, but some of the states they have not acted on that. And even those who have prepared some kind of act based on this, they have not implemented or enforced it as a strict measure. So if we have a policy, we need to have the enforcement at the local levels. Because let us say if this flood plain zoning act will be enforced, uh, it says like zone 1, zone 2, zone 3. In the zone 1, we can do lots of development activities. There is no possibility of coming the floods. In the zone 3, there is a higher possibility of the coming the zone of the flood in zone 3. So we cannot make the structures, or if you need to take the permissions from them, so that you can reduce the losses. But unfortunately, this has not been done. And though there are some reasons for that, like there is an increase in the population, so you need some kind of land for that. People need to have some kind of their earnings, so we cannot do that. So there are issues on both the sides, but I think there is if there is a flood zoning act, some kind of these have been done, we can minimize the losses. Now I will talk about something related to global circulation models or the climate models that I just mentioned in the earlier slides. What we do in these models, we divide whole the earth in the horizontal grids in terms of latitude and longitude, and the vertical grids in terms of heights or the pressures. And once you discretize that, we solve the mass, momentum, and energy equations at each grid, and then subsequently it goes from 1 to 2 and 2 to 3. And that's how the interactions in these systems of the physical process in terms of snow, atmosphere, all these things will happen. And these are generally known as global climate model or general circulation models based on general physics principles of fluid dynamics and the thermodynamics. So they simulate the interaction between atmosphere, ocean, land surface, and ice. And these climate models, they produce huge amount of the data, and several parameters are there with different time steps as well as the spatial resolutions. So spatial resolution can be 100 kilometers, 300 kilometers based on the GCM that you are using, and the temporal resolutions may be hourly, 6 hourly, daily, monthly, based on the climate models that we are planning to use. So based on that, I will discuss one kind of case study with all of you. And in this case study, you can see all the river basins, like Indus River Basin, Ganges River Basin. So Indus River Basin is the river basin ID number 1. Ganges is 2A, Brahmaputra is 2B, Barak is 2C. Then you have a Godavari 3C, 3 river basin ID number 3. Then we have a Krishna basin ID number 4. Then you have a Kaveri basin ID number 5. Then we have a Suvarnrekha basin ID number 6. Then you have a Brahmani and Baitarani basin ID number 7. Then 8th you have a Mahanadi river basins. 10th you have a Mahi. 9th is Pennar and Narmada river basins. 12th number 13 is the Tapi river basin. Then you have west flowing rivers, east flowing rivers. So these are the 24 river basins across the India as per CWC, Central Water Commission classifications of India Bares, because I think there are so many participants in this course. So whichever river basin you can locate, you find out in the which river basin you are here today, and then we will discuss the results of these river basins across the India in the next few slides. So the data we have taken for that is past data from 1975 to 2019, future data 2025 to 2095 that we have taken, and this is the precipitation data of observed daily graded precipitation that we have received from IMD, Indian Meteorological Department, Pune, and then you have a simulated daily graded precipitation data for the future that has been received from NASA Earth Exchange Global Daily Downscale Climate Projections of 21 CME 5 coupled model intercomparison project generation number 5 global circulation model. So data just I mentioned to you, list of the river basins that I mentioned to you. Now let us go to methodology that I would like to discuss with you. Since this course is related to water, so we'll talk only the precipitation. First one is the CDD, consecutive dry days. It means maximum length of the dry spell. Then another index we have CWD, consecutive wet days, maximum length of wet spell. R20, number of extreme heavy precipitation days. It means annual count of the days when daily precipitation is greater than 20 mm. R95, total amount of extreme precipitation. It means annual total precipitation when daily precipitation is greater than 95th of the percentile. So CDD, consecutive dry days. CWD, consecutive wet days. R20, number of 5 total amount of extreme precipitation. That these four indices we are taking up, and I'll give you an example how we can compute these indices. Let us say this is the 1st April 2020 to 30th April 2020. You have a rainfall amount. I just mentioned 1, 2, 3, 4, 5, 30. And 95th percentile, everybody can get it from the Excel. So 95th percentile of this daily precipitation data is 28.5 mm. How to compute the CDD? Consecutive dry days. It means maximum length of the dry spell. Dry day we will consider when the rainfall is less than 1 mm. So CDD, how much of the CDD for this? 0 days. Because we don't have any day where the rainfall is less than 1 mm. Consecutive wet days, maximum length of the wet spell. Wet days when the precipitation is greater than 1 mm. So precipitation is greater than 1 mm for all the 30 days. So I have put here the 30 days. R20, number of extreme precipitation, heavy precipitation days mm, annual count of the days when daily precipitation is greater than 20 mm. So 11 number of days are there where you have more than 20 mm or greater than or equal to 20 mm. So 20, 21, 22 compute, count, then you will get 11 days. R95P, total amount of extreme precipitation in mm. It means annual total precipitation when daily precipitation is greater than the 95th percentile. And what is the 95th percentile of this daily precipitation data at a given location is 28.5 mm. So 28.5 mm, you have a 29 and the 30. So R95P will be 29 plus 30, that's 59 mm. So I hope this is clear with how to compute the CDD, CWD and R20 and R95P. Because that in the next few slides that we are computing for across the India for each of these river basins where we are located today. Okay, so what is the objective that we are trying to achieve in the next few slides? To evaluate the trend of precipitation indices in the past and the future. To develop the spatial vulnerability maps for the for the droughts and floods based on the trend characteristics of precipitation indices. Okay, let us discuss one by one. Are 20 days. Here, this is the India map in the observed time period 1989 to 2019. This is the representative concentration pathways for 4.5. We have taken only one scenario that will show from 2025 to 2055 and 2065 to 2095. And how R20 in terms of magnitude and the trend that we will look like to see. So R20 across the past is this one, observed one, and the future, this is the future, is found to be high greater than 20 days. It means you can see the legends. For northeast region, this is the northeast region, and the western Ghats, this is the western Ghats, and low 1 to 5 days, it means this one, for the western part of India. So part of Rajasthan and part of Gujarat that you can see, this is there. So this is the trend in terms of past and future. And during 1989 to 2019, central and central eastern parts also show moderately high or high R20. It means the greater than 15 to 20 days, this one. So you can see in some parts, central and central eastern parts, that also we can interfere from here. And during 2025 to 2055 and 2065 to 2055, some parts, central and central eastern parts, they are also showing for greater than 20 days. You can have the legend and then mapping can be done. So these are the extreme heavy precipitation days R20. And how's the trend in these extreme heavy precipitation days? Whether they are increasing, decreasing, significantly increasing, significantly decreasing, and how's the sense slope? So during 1989 to 2019, R20 shows both decreasing for Ganga Basin, Northeastern Basin, Godavari Basin, Tapi Basin, and upper part of Indus Basin. And increasing trends, parts of southern India, central eastern parts, and western part of India in the observed trends. What's happening in the future one, 2025 to 2055, R20 shows an increasing trend almost across all the country in the future. So you can see the pink matching for I think most of the countries showing increasing trends. And for positive trends were found out in central eastern parts, and they show significantly increasing trends in some parts. So magnitude and trends. Now what's happening in terms of R95P? If we talk about R95P, attain a higher magnitude of greater than 500 mm. So greater than 500 mm from here to here in the Western Ghats and the northeastern regions. Whereas western part of India, part of Rajasthan, part of Gujarat, they receive lower magnitude, 25 to 250 mm. And the region with lower R95P cover more area in 1989 to 2019 than during 2025 to 2055 and 2065 to 2095. But a spatial pattern remains similar. There is not much change in the spatial patterns, but they cover the more area in 1989 to 2019, low R95 NPP compared to these areas of 2025 to 2055 and 2065 to 2095. How the trend in these? So during the observed period, it means the past 1989 to 2019, around 50% of the country comprising the part of central eastern, western, southernmost, and central region shows a positive trends. R95P shows a positive trend across the country during this 2025 to 2055. Northeastern region showed a significantly increasing trends. You can see it here, significantly increasing trends. And during 2065 to 2095, R95 shows a positive trend across the whole the country. Okay, so what about the cumulative or consecutive bed days after R95P and R20? Consecutive bed days generally greater than 25 days. They are on the Western Ghats and the part of Northeast region, and they are low for 3 to 10 days between in this region of part of Rajasthan and part of Gujarat region or west part of India. During 1989 to 2019, it means the observed period or the past most part of India encompasses moderately low or low CWD consecutive bed days. And during 2025 to 2095, the spatial patterns does not much change. Along with the northeast, western Ghats and the central eastern part, they show high moderately and high CWD. It means for greater than 20 to 25 days and greater than 25 days. How's the trends in the consecutive bed days CWD? Overall trend in the CWD across the country is decreasing. And the CWD shows most around positive trends during 2025 to 2055, and a fewer parts of Upper Ganga Basin, they are showing significantly increasing trends. However, during the 2065 to 2095, it's also showing the increasing trends, except the westmost part shows a decreasing trends. Okay, last one R20, R95P consecutive bed days, and last one is the consecutive dry days. How the consecutive dry days are occurring in the past and the future. So consecutive dry days is mostly high, greater than 200 in the western regions, part of Rajasthan, part of Gujarat, and part of Madhya Pradesh and Maharashtra. And they are low 34 to 100 days in the western Ghats regions, coastal regions, and northeastern regions. If we talk about 1989 to 2019, the regions showing moderately high or high CDD, it means greater than 150 days, cover relatively less area in comparison to 2025 to 2055 and 2065 to 2095. So the spatial extent of high CDD consecutive dry days will increase in the future. And the spatial patterns during 2025 to 2055 and 2065 to 2095 is more or less similar. How's the trend in consecutive dry days? So during 1989 to 2019, CDD shows a general increasing trend, mostly between 0 to 1 days per year across the country. And the CDD consecutive dry days generally shows a decreasing trend across the country during 2025 to 2055. However, few parts of northeast, northern, and central eastern India shows an increasing trends. During 2065 to 2095, CDD consecutive dry days generally shows a decreasing trends across the India. So there is a decreasing trends of CDD in the near future term and the long term in the futures. What are our discussions and conclusions? R20 and R95P, they are showing an increasing trends in major segments of the country in the future, coherent with the previous studies. Consecutive dry days, CDD, shows a following decreasing trends at the end of the century, which is coherent with the findings of RAW-ETL 2014 for monsoon season. The present study about the evaluation of precipitation extremes that improves our understanding of extremes in terms of changing climates, and it will provide valuable additional information for development of disaster mitigation strategies in India. There are few limitations like stationary climate has been assumed. 18 GCMs have been included, more GCM general circulation models can be included. We have included only 2 scenarios, so other 2 scenarios can also be included. And these are the few references where I have mentioned during the presentations. Yes, I think, thank you. And if you have any question, you may ask me now, or you can ask me the later. I will start the second half of this presentation. Uh, so if you have any question, you can ask me now before I start for the second part of this presentation.
Participants, if you have any questions, you can type in the chat box or you can come online.
So, hello.
Yeah,
Yeah,
please
I have
go
a
ahead.
question, sir. Yeah,
Go ahead.
I'm speaking. Yeah, I'm speaking from Manipur, sir. I myself is Anil Kumar Sharma, sir. Just now you have discussed the general trend of the rainfall pattern in India. It's going to be changed. So why in your study there is no any consideration of the vegetative cover influence upon the climatic change? Parameter is not there. How it is if we did not consider the vegetative cover influence upon the climate change, how can we rely on upon that prediction, sir?
I think you have a very good question, and that is the limitation of this study. So for vegetation cover, we have another study how it is impacting the climate change. Obviously, there is an impact of the vegetation cover on the climate change, like you have forestation and other stuff, and that also to be included. But here we have taken the general circulation models, and based on that, we have taken the these projections. So a comprehensive study, including the vegetations, that also may be included to have a more realistic results.
Okay, so thank you.
Anybody else who's having any question or doubt? Sir, I have a doubt.
Please go ahead. Please go ahead. Yeah, it's a discussion forum, so we will learn with each other.
So we have processed the data which we got from specific authorities, right? But what was the basic software that was used for processing this data?
It's a simple MATLAB code programming.
Okay.
So we have prepared a code in the MATLAB, and that we use to process the data because this data is very huge.
Yes, sir.
Yeah. So and in terms of temporal variation, in terms of spatial variation, data is very huge. So we use the basically we use the server, and it took some time to run it.
So any other participants would like to interact? I think we should proceed with the second part, sir.
Sure, sure. Go ahead.
Your precious time to us.
Yes, anybody wants to? Yes, sir. Sir, Amit sir would like to interact.
Yeah. Please go ahead. Please go ahead.
Sir, thank you very much, sir, for giving your precious time
Thank
to
you.
us, sir.
Thank you. Thank you. Thank you.
कैसे हैं, sir?
बस बढ़िया बढ़िया सब अच्छा चल रहा है.
जी.
Okay, so we'll go to the next one, and I think I'll discuss very important things. Probably you all will enjoy with this. This I just discussed the June 2013 events where in the Uttarakhand in the 72 hours we got around 38 centimeters of the rainfall, and there are huge losses and all. In the Chennai, I just mentioned like 48 hours you got 48 centimeters of the rainfall. In July 2005 in Mumbai, in 18 hours you got 92 centimeters of the rainfall. And okay, so I will discuss some very important concept, the atmospheric rivers. Uh, like we have rivers in the land, so there are few rivers in the sky as well. and these rivers are known as atmospheric rivers. So I will discuss the physical, technical, and the scientific aspects of these rivers. Okay, so 1 second. Yeah, this is the US one, understanding physical aspects, technical aspects, and the scientific aspects. Okay, so have you ever thought that rivers are only on the land? Rivers are also in the sky. And how do we know them? Or what is the name of these rivers? So I think you can see this video where the moisture plume is going from the ocean towards the western coast of US. This is the US and this is the western coast of US, and from there, from the Pacific Oceans, you can see once more. This is the moisture basically, and this moisture is reaching from the ocean to the land, and here it is precipitating. So here you are getting the higher amount of the rainfalls. So, and this moisture plume we will name as atmospheric rivers, and this we will try to understand how it is impacting our water quality, water bodies, and many other stuffs. Okay, so atmospheric rivers, they are the relatively long. You can see it here in this picture, relatively long and the narrow regions in the atmosphere, like rivers in the sky, and they transport most of the water or water vapors outside the tropics. And how they will transfer in terms of vapor transports, integrated vapor transport, IVT, this term I will explain to you. And here IVT is given from 150 to 700 kg per meters per seconds. So these atmospheric rivers, they are relatively long and narrow regions in the atmosphere, and they are like we have a river on the land, so like rivers in the sky, and they are known as atmospheric rivers. So what is the atmospheric rivers? This is the video of few seconds that I will like to play. So there are no sounds. Okay, so I hope got some kind of idea with atmospheric rivers. So I'll discuss now the significance of these atmospheric rivers. AR is nothing but atmospheric rivers. So strong atmospheric river, they can carry more than twice the volume of Amazon rivers. Okay, now you can imagine the magnificence of these rivers. They can carry the volume of the water more than the Amazon rivers. And how the magnitude? Atmospheric river can approximately 400 to 700 kilometers wide. So width is around 400 kilometers to 700 kilometers, and length thousands of the kilometers long on an average. How their connectivity? They have the close linkage with the precipitation patterns at several regions across the world. and around 1/3 to 50% or 1/3 to 1.5 of annual precipitation on the west coast occurs in just few atmospheric river events. And what are the impacts they have? Water availability, extreme precipitation and the flood, global climatology. So magnificence, magnitude, connectivity, and the impact of these atmospheric rivers. So they are the bigger than the biggest. And how biggest? How magnificent an AR can be. Length of the Ganga River is around 2,704 kilometers. Length of the Amazon River is 6,575 kilometers. And strong atmospheric rivers in the sky can carry more than twice the volume of the Amazon rivers. With these figures or data in your mind, you can imagine the voluminous nature of these atmospheric rivers, how much amount of the water they are carrying. There are thousands of the kilometers long with average width of 400 to 700 kilometers. So length is thousands of the kilometers. Average width is around 400 to 700 kilometers. So that's how the magnificent they are. Impact, close linkage with the precipitation patterns at several parts of the world. 30 to 50% of annual precipitation on the west coast occurs in just few atmospheric river events. Medium for availability for the beneficial rain and ice, causing devastating floods and thus influencing the global climatology at local, regional, and global scales. You can see the several of the media coverage in these atmospheric rivers. Atmospheric rivers can cause $1 billion damage a year, study shows, and are getting worse. Atmospheric rivers fuel most flood damage in the US based climate change and will make them worse. Atmospheric rivers other than over the Atlantic blamed for torrential rain. Atmospheric river storm can drive costly floodings, and climate change is making them stronger. Pineapple Express storm will bring more flooding and snow to the west. So one of the atmospheric river has been named as a Pineapple Express. Okay, there are few things that we get to note while we go for atmospheric rivers. AR terminology is generally used for moisture plumes with some kind of thresholds of two things: integrated water vapor and integrated water vapor transport, IWV and IVT. Not all the AR gives the heavy precipitation. For that, some kind of strong winds, moisture, and lesser stable environment is required. And how we can characterize the strength and impacts of these atmospheric rivers. So American Meteorological Society has been ranked from 1 to 5 in different category with this natures of these atmospheric events. So if you can see this picture given in the table, this is the rank. First rank is given for this AR category, atmospheric river category, weak, and the primary nature of this is beneficial. What is the example for that? On February 2, 2017, AR hit California, lasted 24 hours at the coast and produced modest rainfall. It means in 24 hours you got a modest rainfall that is primarily beneficial. At rank number 2, AR category is moderate, so mostly beneficial but also somewhat hazardous. An atmospheric river on November 19, 2016 hit Northern California that lasted for 42 hours at the coast and produced several inches of the rainfall that helped replenishing the low reservoirs after a drought. So this is somewhat beneficial. Rank number 3, you have AR category is strong. Nature is balance of beneficial as well as hazardous. An atmospheric river on October 14, 15, 2016 lasted 36 hours at the coast and produced 25 centimeters of the rain that helped refill reservoirs after a drought, but it also caused rivers to rise just below the flood stage. So here you got modest rainfall, here you got several inches of rainfall that replenishes the low reservoir here, that helps the reservoir but also rise up to the just below the flood stage. And then you have a rank number 4, extremes AR category. They are mostly hazardous. And AR on January 8 and 9, 2017, that persisted for 36 hours, produced up to 35 centimeters of the rain in Sierra Nevada and caused at least dozens of the rivers to reach the flood stage. So you can see that many of the rivers, they are reaching on the flood stage due to this extreme AR category. Fifth one is just opposite of the first one, exceptional, and this is primarily hazardous. On December 29, 1996 to January 2, 1997, AR lasted over 100 hours at the central California coast, and the associated heavy precipitation runoff caused $1 billion in damage. So you have a weak, moderate, strong, extreme, and exceptional, from primary nature to the beneficial to hazardous, and there are few examples for our better understanding. Okay, how is the distributions of the ARs intersecting with the coastal line? It means here you can see the frequency, it means days of the year, but the 5, 10, 15, 20 of atmospheric river landfalls for the period from 1979 to 2018. Here you can see this map of India and rest of the whole across the world map you can see with latitude and longitudes. Availability of atmospheric rivers intersecting the coastal line at 6 hourly time steps. Landfalling ARs are more frequent in west coast of North America, southern South America, and Europe. Okay, why to study the AR? We should have early flood forecasting warning systems, weather forecast, water resources management, flood risk management, because they are carrying high amount of the high voluminous nature of the water vapor. So we should know how much water is there and what is the probability of the landfall and where it is the probability. So having understood the physical aspect, let us go to the technical aspects. How I can compute the IVT and IWB, integrated water vapor transports and integrated water vapor. We have a wind velocity and you have an altitudes. So wind velocity and altitudes, and then what we can do, we can take this water vapors with respect to altitudes and sum vertically, you will get integrated water vapors. And if you multiply with both of them, you will get water vapor transports with sum vertically, you will get integrated water vapor transport, IVT. So IWB, you can sum vertically the water vapors, and in water vapor transport you need to multiply with wind velocity into water vapor. These are the mathematical formulas for IWB. 1 upon G from 1000 hectopascal to 300 hectopascal QDP, and IVT, integrated vapor transports, square root of 1 upon G 1000 hectopascal to 300 hectopascal QUDP whole square plus 1 upon G 1000 hectopascal to 300 hectopascal QBDP whole square. Where QUB, they are nothing but the U and B are the zonal and meridional winds, and Q is specific humidity. dP is the difference in the pressure between two adjacent pressure levels. The thresholds for IVT, integrated vapor transport, popularly adopted as 1000 kg per meter per second. And for IWB, we will take 20 mm for distribution and AR. So these are the thresholds that I mentioned in the previous slide, because there should be some kind of thresholds. And the maximum moisture lies in the troposphere layer of atmosphere, which ranges from sea level to 10 kilometers upwards. The 1000 hectopascals pressure level is a few meters above sea level, and 300 hectopascal is just ascended part of the troposphere, somewhere around 10 kilometers from the ground surface. So that's how we are doing the integration between 1000 hectopascals to 300 hectopascals. We have also understood here the thresholds of integrated water vapor and integrated water vapor transports. So what are the data that we required and that we will use for the study? So we need specific density data, zonal bends and meridional bends. The spatial resolution is 1.5 degree by 1.5 degree for each of these three parameters, and the pressure levels are 21 levels that we will divide from 1000 hectopascals to 300 hectopascals, and the source is ECMFW or ERA entering. With this link we can get the data. How we'll do the zonal IBT? You can see the 1 upon G 1000 hectopascal to 300 hectopascal QUDP. So you can do the integration and you will get some kind of these pictures. Some similar things for meridional IBT, you'll get some kind of pictures 1 upon G 1000 hectopascal QBDP. So zonal IBT and meridional IBT. And how can I characterize the atmospheric rivers? Because AR is a combination of moisture and strong winds. The threshold criteria for characterizations of AR depends on various factors such as location for the area of interest, seasonal variation, and landfalling probability. So for that we need to detect the ARs. ARs have to be detected for each of these grid cells based on this magnitude thresholds. Then you need to find out the directions, length to width ratio for these each grid cell in the objects, and then we need to identify the AR landfall probability. So here you can see the IBT square root of 1 upon G 1000 to 300 hectopascal QUDP whole square plus 1 upon G 1000 hectare to 300 hectopascals QBDP whole square. 85th percentile means map of for the 5 months for each of these 12 months at each grid for all the time steps for each month. So this is the map for IBT of 85th percentile for month of May, June, July, August and September throughout the time period of 1979 to 2018, and then you will get these kind of moisture plumes. So we can detect the shapes, and what are these criteria? IVT should be greater than 85th of percentile, length should be greater than 2000 kilometers, length to width ratio should be greater than 2, and there is some kind of criteria for mean meridional IVT. And you can see here the different shapes of these atmospheric rivers. For North America, for South America, for North of Africa, south of Indian Oceans, and then you can see these all kind of shapes from the detections that we got for atmospheric rivers. We have understood the physical aspects, technical aspects. Let us get the scientific aspects of atmospheric rivers. So here you can see the atmospheric rivers summary in changing climate under warming conditions or representative concentration pathways. Red and blue symbols reveals increase and decrease. It means it's increasing. Gray symbols indicate the unknown changes, and background symbols that will give you the frequency increase. So if you talk about the South Africa, these two steps like frequency, location, precipitation, extreme precipitation, snow and ice, flooding, and air frequency increases. So flood frequency and flood extremes, they are expected to increase in Southern America. Then you have in the Europe, Greenland, North America, East Asia, New Zealand, Southern America, and Antarctic. How these AR is happening in terms of frequency, location, precipitation, that we can get it from here. Okay, and there are few more studies on how the atmospheric rivers and large scale climatic oscillations are related, that I will not go into the details, but there are some kind of relations that is there in these large scale climatic oscillations and the atmospheric rivers. So global distributions of atmospheric river and associated large scale water vapor transports, it indicates there is a critical role of atmospheric rivers in shaping the global water cycle. And AR landfalls occurs in all continents and major islands, which has implications for extreme meteorological and hydrological events, including water resources in many of these locations. And more devastating atmospheric rivers, they are expected in the future as per projections of the global climate models with global warmings. So more focus for better understanding of these atmospheric rivers for developing a robust system for water resources management and risk management are required. So with this, I think I will like to end, and thank you very much for listening. If you have any question, please let me know.
Participants, you can post your questions in the chat box or you can come online. Anybody would like to interact with sir? Sir, the atmospheric rivers can be analyzed with the help of remote sensing applications?
Some of the data is available this on ERA interim that I link I showed to you. So once you get the specific density, zonal wind and meridional wind, the data we can get it from there, and then we can analyze atmospheric rivers.
So we need to get the data from the remote sensing centers?
Yes, yes. This data is freely available.
Okay, sir. Sir, is similar air quality data also available on remote sensing centers?
Some kind of air quality data you can get, not all.
Okay, sir. So there's a question, what is the character of atmospheric rivers and it is useful for human?
What is the character of AR? I think on the land you have a river, right? Ganges, Brahmaputra. Similarly, in the atmosphere we have a river, and that river is named as a. And if you are asking in terms of physical, I just mentioned in terms of length, width. So length may be few thousands kilometers, width is around 400 to 700 kilometers. That's the characteristics of AR. And it is useful for the human. Yeah, they may be primarily beneficial to the primarily hazardous based on the rank that we have showed from 1 to 5. If you are getting the higher amount of rainfall, and that will be obviously hazardous. If you are getting some kind of reasonably lesser amount of rainfall, that will help you to replenish the reservoirs. That is useful. So that's how it's useful and not useful for human and others.
So anybody else who's having any doubt? So, sir, I think there's no as such question raised from the participants. And if they have in later case, we will contact you via the email. And I really thank you for taking out time for the informative session and specifically the atmospheric rivers. That was a new concept for us, and you enlightened us over that. Thank you so much for accepting our request and honoring us by coming over online for this session, sir.
Madam, one more question is there, I think.
Sir, can we transfer this AR to desired location? That's what.
I don't think so. I don't know basically. We don't
Yes,
have,
sir.
we don't have a
There was a
technology.
concept. There was a concept that we can specify the location where precipitation can occur. Is that an actual concept?
No, we
Can it
don't have
happen
that. I
actually?
think we cannot transfer to desired location. No, I think probably it will take another few decades to have that kind of technology.
Thank you so much, sir.
Okay, thank you very much, Dr. Devanshi and IPS Academy for inviting me, and thank you so much. Yeah.
Thank you, sir.
Thank you, sir.
So the next session will be starting at 12. We will have a break of 10 minutes and we will be coming back again at 12 p.m.